Hi there. So today we are solving this problem 3003, maximize the number of partitions after operations. We are given a string s and integer k. We are allowed to change at most one index in s to another lowercase English letter. And after this, we have to do this operation, this below operation. So what is this operation? We have to choose the longest prefix of s containing at most k distinct characters, and we have to delete the prefix from s and increase the number of partitions by 1. The remaining characters, if any in s, maintain their initial order. And this operation we can do multiple times, and after this our string will be having no letters, and we have to find out the maximum number of partitions that we can do in the string. So let's try to understand this with the help of an example to get a clearer understanding of this. So let's see, we have this string given, and we have this given k. So we have to take two unique characters in a partition, that is why k is given. So if we will start counting unique characters for each index, then this is what we will get. For character A, we have only one unique character right now. Okay, so we have one in this. Then we'll add C. Now we have two unique characters. Then we'll again add C. Now we have still two unique characters because C and A are completely unique. We'll add C, again still we have two unique characters. We will add A, still we have only two unique characters. So this is how we are getting the unique characters for each index in the array. If we will take another example, and here k is equals to 3, that doesn't matter. Let's just see how we are trying to get the unique characters at each index. So for A it is 1, for A it is 1 again because it's the same character. For B it is 2, for A again it is 2 because A has already came before this. So for A again it is 2, for B it is 2. Okay, so this is the unique characters array kind of for each index in the string. Okay, we are allowed to change one character in the string to any other character, and we have to maximize the number of partitions that we can have. Okay, so for this example, maximum unique characters we have is 2. Okay, so no matter what character we will change, maybe we will change A to C or B to Z, whatever, our overall string will have at most these three characters which are unique, right? Even though we will change it, still we will have only three unique characters. Okay, so that's why the answer for this will be 1. Now let's see with this example what are the possible cases for this. Let's try to change C to something because it looks that there are multiples of C. So let's say if we change this C to B, then we will have this type of unique characters. Okay, so for A it is 1, B it is 2, C it is 1 again. So now here is the catch, how we are calculating the unique characters. Because k is 2, let's say if we got this one unique character, then two unique characters, as soon as C comes in the picture, we will get three unique characters. Okay, three unique characters, and we have to partition after we get two unique characters. So till the point we are not reaching this C, the entire string from on the left side is giving us one partition. Okay, so that's why this is the one partition, and from C onwards we will again start our unique characters count. Okay, so for C it is 1, for this C again it is 1, for A it is 2. So we are reaching to this partition and this partition. So in total we will have two partition if we will change this C to B. Okay, so this is clear. So let's say if we change this character to something else, it doesn't matter, we can change it to Z or X, whatever. Let's say if we change this character to B, then how will our count change? Let's see. So for A it is 1, for C it is 2. As soon as we go to B, our count will be 3. Okay, unique characters count will become 3, but we don't want 3, we just want 2 in a partition. So we will break it. We will break the string from here. So here it is 2, and from B again we will start the count from 1. Okay, so for C again it is 2, and for A again it is coming as 3. So BCA has 3 unique characters, right? So we will again break it from here, right? And for A again we have only one unique character. So overall we are able to partition the string into 3 sides, and this was only possible if we change this C to some other character. Somewhere we have to consider all the possible cases that we can have with our string. Okay, so we have to check if we can convert A to any other possible character from A to Z, and then we have to check for our answer. Similarly for C we have to check if we can convert it to either A, B, C, D till Z. We have to check all the possibilities again for this C as well, this C as well, and this A as well. Okay, but as soon as we consider a change, we will not consider the change for the rest of the characters, because at most we can take only one character change in our string. Okay, so let's see how we will actually do this. We'll start by the 0th index. Okay, and whatever unique count we have considered so far, okay, that we will have. And if we have changed any character or not previously, that we will also consider. Okay, so initially we will have index 0, and unique character so far is 0, and change allowed is 1. Okay, so we are allowed one change in the start. We can take this change or not take this change according to our answer, but we want to enumerate all the possibilities here. Okay, so let's say this is the string ACCCA, and this is the helper function that we are calling, and we are going to enumerate all the possibilities. There are two things. So let's say we did not change it and we did change it. Two possibilities. Okay, so if we did not change it, what we will do is, so we will increase the index value to 1. We will update the unique count as well, and this change we did not do, so we will pass 1 as well here. Okay, but what if we change the character? We have 26 possibilities to change the character, so we have to consider all the possibilities. So we can change A to A. I mean, that doesn't make sense, but yeah, so we have like 26 possibilities. So A can be A, B, C till Z. These are all the possibilities that we have. And if we are considering these possibilities, so what will happen is, so the next index will be 1. Unique character so far is 1 because we have considered A as well, and we have done the change, so we are going to send 0 to the change allowed. Okay, so this is how we are going to enumerate. Let's see how it proceeds for a proper example. Okay, so if we are given this string, we are not allowed change, we are allowed change here, we are doing this change. Let's say we are building this answer, we did not change it, and then we came to this second index, and then we did not change it again, then we came to this third index, and so far what happens is we have got two unique counts, right? A and C are both unique, so the unique count becomes 2. Okay, now we are at this place in our string. Now what we can do is, either we can not change again, or we can change. So let's say we did change it, and there are 26 possibilities to change it. So let's say we pick this ACCA and we change this C to a B. Okay, so what will happen is, after we convert it into B, now we have, if you will notice, the total unique count is 3. Okay, but K was given as 2, so we have gotten one partition just before this change, right? So the previous string gave us 1 as answer, one partition as answer, right? And this particular string, the remaining string, we are going to again call this helper function on this. How we will call it? So we will definitely call it for the next index, and here now we have updated the unique count to 1. Why? Because now we are only considering this previous count was 2. We are not going to take it because again this partition is done, so we are going to start from this one, and for this character we have got one unique count, and now we cannot change anymore, so we have 0 in our change allowed. Okay, so this is the helper function that we are calling. Now let's see how is it actually proceeding to the answer. So we were here ACBCA, and after this change we have gotten this, and let's say we are proceeding with this character, right? So we can not make a change, or we can make a change. Now here we cannot actually do change because we have this change allowed as 0, right? This one, so we cannot actually change, so this branch is automatically pruned. We have only this possible branch, we cannot change the character anymore. So now we have ACBCA, and what we will do is, we'll go to the next index. This is the next index, and for this index value we have to add 1 to the unique count, because B and C makes 2 as unique count, and 0 because we are not allowed change. Okay, we are here with this string, and we are at this index now. So for this index again we cannot change because this is pruned. We are not allowed to change. But if we will not change, what will happen is, BC was there, and if we will add A, so because of this addition of A, the unique count becomes 3. Okay, but the K is 2, so again we can partition. Before this index we can do a partition as well. Okay, so if we will partition before this index, whatever the string we had, what we will do is, we will add 1 to our answer. Okay, and we will call helper function on this, whatever is remaining. If we will call on this, so we will call on the next index which is not there, and this 1 is because of this A, we are counting the unique characters from now onwards, and 0 because change is not allowed. As soon as we will get this, our string length is completed. That means we are at the base case, and now we can simply return 1 for whatever the string that we were building currently. Okay, so this was a string that we were building currently, so we have to have one partition for this as well, right? So if you will consider this in this example, it may not be clear, like we have only one character, but if you will consider this example, let's say we have A, C, B, C, C. For AC we have one partition, and for BCC again we will keep on going until we reach the end of the string, and this will give a base case, and for that we have to return 1. That's why we are returning 1 here. Okay, so there is a way that we can keep the unique characters count in a bit mask. That will be very easy for us to handle. So let's say we have like nothing in our string. Let's say our string is empty, then we can take 26 bits and all the bits we can set to 0. Let's say we have only A in the string, then we can set the 0th bit as 1. Okay, let's say we have B, then we can set the second bit, this first bit, as 1. If we have A, B, C, then we can set these 3 bits as 1. Okay, if we have A, we will keep on setting this bit as 1, and this will not change anything. So this is how we are able to calculate the number of unique characters with the help of bit mask. Okay, so if we have 26 bits, and if we are setting each bit based on the character that it corresponds to, so the total number of bit counts in this bit mask will give us the unique characters in that string. Okay, so this is how we are making our code little bit simplified with the help of this 26-bit mask. Okay, now let's see how recursively we are going to solve it. We are definitely going to call a helper function with the index, bit mask, and change allowed. So this bit mask is basically representing how many unique characters, right, in the string. Okay, so this is how it is helping us. Now if we are at the base case, that means we are at the string length, we will simply return 1. Okay, because whatever we were building, that is also a partition. Okay, so let's say we have this ACCCA string. Okay, and for A, this is the bit mask, right? We have set this this bit as 1. For C, this is the bit mask, we have set this bit as 1, and the total bit mask for this and this will become, if we will OR this, right? So this is what we are taking care in the bit mask. Okay, so to find out what position it is at the bit mask, we have to find the bit position of that character. Let's say if it is A, then if you will minus this with A, it will become 0. Let's say if it is Z, if you will minus this with A, it will become 25. This is how we are trying to find out the bit position for that particular character in our bit mask. Okay, so if we found a bit position, then we will simply OR this with our bit mask. So let's say our bit position is 3. So that means we want something like this in our answer. Okay, so to get this, we have to shift 1 by 3, and that's how we are getting to this position. Okay, now we have to consider two cases, of course. First is without changing, and second is changing. So if we don't change the character, what will happen is we have to find if the current new mask has more than k bits. That means the previous one has one partition. Okay, so if the previous one has one partition, that means we can add 1 to our answer, and we have to have this helper called on from this particular index and onwards. Okay, so for next index and for this particular index, we will find this bit mask. So we are sending this as our new bit mask because we will discard whatever was the previous bit mask, right? And we will get this new bit mask for this current character. Okay, that's why this one and bit position, and change allowed is still whatever it was given to us, we will keep on taking care of it. Otherwise what will happen is, if we are not getting any answer, we'll keep on continuing this. Okay, we'll keep on going index plus 1 with whatever the new mask that we got. We are not changing mask here, we are only changing mask as soon as we get one partition, and this change allowed again will be same. The second case is when we change the current character. So if we change the current character, we can only change it if it is allowed first of all. So if this is still 1, we can consider all the possible characters from 0 to 26, from A to Z. We can consider all the possible characters. What we will do is we will try to find the new mask with the new character. So this will be the new mask. So current mask and the bit position of the new character. Then we will try to see if we are getting the unique count greater than k. If we are getting it, that means we can update our answer to whatever answer we have gotten so far, or we have definitely gotten this one partition, so we'll add 1 for this and this helper function for the next index. Okay, the same thing. Otherwise, if this is not the case, we are not still at the partition, we will continue with whatever we will get. Okay, so now we have to consider that we are taking this as 0 because we have used our change, so we will use it as 0. After the end of this, we will return our answer. We have 3 variables, right? These 3 variables changing, so we have to have some kind of a 3-dimensional DP array to store our states for every index, bit mask and change allowed, because they are definitely going to get repeated over the course of our recursive function. I actually tried to do with a 3D DP approach, but it led to memory limit exceeded, and then I dig deeper into it, then why did it happen. So if we have this DP array here, that means we are going to have n length for indices, and for here we are going to have 26 bits number here. So let's say this is the maximum number that we can get, which was this. So this is the place, and for change allowed we have only two possibilities, 0 or 1. So we'll have 2 places for this. Okay, so if we will try to calculate this, and even if n is equals to 10, which is not in our case, 10, it is 10 to the power 4, even if it is n is equals to 10, we will still get so many possibilities for our DP array, 134 million possible integers, and that will lead to nearly 5 GB of memory in our DP array, which is too much because Leetcode has memory limit of 256 MB only. So that's why this is going to fail with MLE. I did try another approach with hash map. So in hash map, actually what we can do is we can either take string to integer mapping. So what this string will be, so we are basically doing index, bit mask and change. So these three things we are taking. So what we can do is we can have our index, our bit mask and our change added as string, and we can have whatever value this is having in our map. Okay, so the string we will get is, let's say our index is 0 and the bit mask is, let's say, this one, and the change is 0 or 1, so this is the change. Then this string we can store in our hash map, and we can save all the states of DP with the help of this string. That is one option. Other option is we can take a long variable, and now here the bitwise DP comes into picture. So we have these three things that we want to store. Okay, we know that change is just 0 or 1, so it is going to take 1 bit. Bit mask is 26 bits, we know this already, and index is 10 to the power 4 at max, so it is 14 bits at max. So 14 bits is for index, 26 bits for bit mask, and 1 bit for change. If we will store everything in a bitwise manner, we can have a long variable which will be able to store all possible states of a DP. Okay, so this is how we are storing things. We are going to have this 0th bit reserved for change allowed, 26 bits for all the bit mask, and 14 bits for our indices. Okay, so if we will do this, we'll be able to handle all the DP states. What we have to do is, for this index, we know that just before that there are 27 bits. So whatever index we are having, we have to left shift it by 27 bits to get to the original bit position where we can actually store the indices. Same for the 26 bits of bit mask, we have to left shift it by 1 to properly store it in our long integer. Okay, so we have to do this index left shift by 27, bit mask we can left shift it by 1, change allowed, actually this value is just 0 or 1, so we can directly OR this. Okay, and if you will take this example, this is index 1, bit mask is, let's say, this, change is, let's say, this. What will happen is our key will become this. So for index 1, this is the one which is here, bit mask is this, so this is the entire bit mask, and this change is 1, so this is the change. Okay, now let's try to see in the code how everything just combines and works together. We will start with a recursive solution, and then we will modify that to the bitwise DP approach. Okay, so we will simply call this helper function, and this will calculate us all the possible cases, and it will return us the maximum partitions that we can achieve. Okay, if we have reached to the end of the string, we will return 1 because we have to consider the current partition that we were handling. Okay, and otherwise we will try to get the bit position for the character, whatever character we are dealing with. We'll try to get the new bit mask. This is just ORing it with the original bit mask that we are getting here, and after that we will calculate our answer. Initially, let's just assume that our answer is 0, and we will try to calculate if the bit count is greater than k. If yes, we found an answer, we are going to add 1 to our answer, as well as we'll call the helper function in the remaining string. Okay, what is the remaining string? Index plus 1, and this is the start of a new bit mask. We are only going to consider our current character for the next bit mask, and can change is still the same. Okay, if that is not the case, we are going to continue this with our helper function. We are going to calculate this for the next index. We are going to take the new bit mask into account now, and can change is again the same. If we are considering the change, so first we have to check if there is a can change. So we have to check if can change is there. So here I have taken a boolean variable. You can also take 0 or 1, that does not matter. So if can change is there, we are allowed one change. What we will do is, we will consider all the possible cases for a character change. We will calculate the new mask. We will calculate the number of unique counts in this current string, and if that count is greater than k, that means we can partition it, and that means our answer will be 1 plus whatever the helper is going to give us next. Okay, this max we are using because we never know what we are getting from here. Okay, and same with this, if we are not getting any answer yet, we are going to use a new mask, and here we are sending the false because we are not going to change the character anymore. We are only allowed one change, and at the end we are returning the answer. Okay, so if we will try to run this and submit this, this solution is going to give us time limit exceeded. Let's try to see that. Okay, so only 7 test cases are not passing. Anyways, let's try to see the better approach for this solution. So this is a better approach for this. We have taken string here. Again, this is not very efficient, but this will get submitted. So that's why we are taking this. This DP one, this did not get submitted, and it failed even in the very initial test cases as well. So this is why we cannot use the 3D DP approach here. We only are changing these 3 variables. That's why we want something that can uniquely represent these 3 variables and their values. So what we will calculate is, we will calculate this key, and this will be index and plus bit mask and change allowed. Okay, so this will be a unique key, and if our map contains this key, we will return whatever is in the map. Otherwise, the same thing that we were doing, we will calculate the new bit mask. We will check if the integer dot bit count is greater than k, and we will continue doing the helper function thing again, the same one here. At the end, we are just putting our answer in the map for future DP states if we get it repeated. Okay, so this is also submitted. Instead of a string, we can use a long variable, and what we can do is, we have to have, when we are calculating this key, first of all, this key is going to be long. So this is a new key which we are taking. So from the string to the long approach, this is the only change which we are doing. And at the end, we just have to put it into our map for further considerations. Let's try to submit this as well. Okay, so I think that was all for this video. Thank you for watching. I'll see you next one. Bye bye.